All right, good morning, everyone, and welcome to this briefing for the upcoming launch and historic mission for NOAA's Space Weather Follow-on Lagrange 1 Satellite Observatory, also known as SWFO-L1. I'm John Bateman with NOAA Communications, and I'll be facilitating today's briefing. If you have additional questions after the conclusion of the briefing, I can be reached by email at nesdis.pa@noaa.gov. That email address is also located on the media advisory. Today's briefing will feature a short introductory video highlighting the SWFO-L1 Observatory and its groundbreaking mission. Then experts from NOAA, NASA, BAE, academia, and industry will provide their perspective on the technology and partnerships that are critical to this mission, and also discuss the benefits SWFO-L1 will provide once in operation. Lastly, our experts will be on hand to answer questions from members of the working media during our question and answer session after their presentations. I also wanted to note that at the bottom left-hand side of your screen, we have a box for more information that includes some helpful links, including a SWFO-L1 press kit with videos, images, and quick SWFO-L1 facts for the media. SWFO-L1 is NOAA's first satellite dedicated specifically for and fully dedicated to continuous operational space weather observations. It is scheduled to lift off in September 2025 aboard a SpaceX Falcon Heavy rocket from NASA's Kennedy Space Center in Florida. Once in orbit, SWFO-L1 will be positioned toward the sun at Lagrange point 1, which is approximately 1 million miles away from the Earth. We will get to our panel of experts shortly, but first we have a short video that will give you more information about the revolutionary SWFO-L1 Observatory and its mission.
Meet SWFO-L1, NOAA's first purpose-built space weather observatory. From its unique vantage point at Lagrange point 1, 1.5 million kilometers from Earth, SWFO-L1 keeps an eye on the sun's corona 24/7 without interruption to provide early warning of solar storms heading our way. The spacecraft's crown jewel is its compact chronograph, its eye on the sun. Just like the GOES-19 chronograph, it allows SWFO-L1 to detect even the fastest coronal mass ejections right as they happen. The spacecraft is also packed with a suite of new instruments that allow it to make real-time measurements of the solar wind's velocity, density, and temperature, and variations in the interplanetary magnetic field, all to provide better forecasts of incoming space weather than ever before. All of that technology floating out in space on SWFO-L1 works together closely to keep us safe back here on Earth. NOAA's Space Weather Prediction Center in Colorado is constantly on the alert, using all the data SWFO-L1 collects to develop and communicate real-time forecasts and warnings to industry, government agencies, and the public, so they can take action before the storm arrives to minimize its impact. Those actions might include putting satellites into safe mode, rerouting polar airline flights, sheltering in a safe area on the International Space Station, or changing loads on the power grid. In our increasingly technology-dependent world, we're more vulnerable than ever to solar storms. But at the same time, our fleet of space weather satellites is aging out of service after many years of work in the harsh environment of outer space. That's why SWFO-L1 is the first of a new generation of sun-observing spacecraft that NOAA is launching. SWFO-L1 will use its cutting-edge observing technology to provide NOAA forecasters the best and most reliable data available, and ensure our nation doesn't go a minute without eyes on the sun, our life-giving but turbulent neighborhood star.
All right, and with that, I will introduce our experts today as they turn on their cameras and microphones. First will be Irene Parker, the NOAA NESDIS Deputy Assistant Administrator for Systems and performing the duties of the NESDIS Assistant Administrator. Our second speaker is Richard Ullman, Deputy Director and current Acting Director of NOAA's Office of Space Weather Observations. Next will be Dimitris Vasiliadis, Program Scientist for NOAA's Space Weather Follow-on Program. Our next presenter will then be Shawn Dal, Service Coordinator and Senior Space Weather Forecaster at NOAA Space Weather Prediction Center. After Shawn, we'll hear from Jim Morrissey, NASA's SWFO-L1 Flight Project Manager. Then we'll hear from Jim Maschiarelli, the SWFO-L1 Project Manager for BAE Systems. Following Jim will be Edward Uton, Assistant Professor with the Geography and Geoinformation Science Department at George Mason University. Then we'll hear from Captain John Dudley, Director of Operations and Pilot for American Airlines. And finally, we will hear from Terry Griffin, Professor and Extension Economist at Kansas State University. And we will now kick off our presentations with Irene Parker from NOAA's Satellite and Information Service. Irene?
All right. Thank you, John, and good morning, everyone. We're just a few weeks away from the launch of SWFO-L1. For years, we've now relied on satellites, some which are well past their design lifespan, to give us crucial warnings about solar storms. These warnings are the first line of defense against the potentially devastating effects of space weather. Imagine a massive surge of energy from the sun that could overload power grids, knock out GPS, or disrupt air travel. These are all the threats our SWFO-L1 observatory is designed to combat by providing continuous, high-quality data, similar to how ocean buoys detect an incoming tsunami. It can't stop an incoming threat, but it can give us time to prepare. SWFO-L1 will give our forecasters at NOAA Space Weather Prediction Center the advanced tools they need to protect our country's critical systems. This launch is not just about a new satellite. It's about building a more resilient future, ensuring that technologies we depend on are protected from the sun's most extreme events. With the mission in mind, NOAA is already looking ahead to our next generation of space weather satellites, a program called Space Weather Next. This ambitious program is designed to provide long-term continuity and enhance space weather monitoring capabilities well into the future, ensuring our nation's technological infrastructure remains protected. NOAA is working closely with Congress and the administration to fund the Space Weather Next program, with the launches of 2 core observatories to Lagrange Point 1 targeted for 2029 and 2032. Ensuring the continuity of these critical services provided by SWFO-L1. While it's important to remember that SWFO-L1 is a NOAA mission, it is also critical to note that just like with NOAA's previous satellites, our partner NASA has played a critical role in bringing the satellite to the launch pad. In fact, the NOAA-NASA partnership has successfully sent many environmental satellites into orbit during the last 50 plus years. And we'll be hearing more from our NASA SWFO-L1 Flight Project Manager later in the briefing. So thank you, and go SWFO-L1. And with that, I'll turn it over to Rich Ullman.
Well, thank you, Irene. As Deputy Director for Space Weather Observations, I'm excited that we learned this morning that launch is now confirmed for September 23. And to tell you that SWFO-L1 represents NOAA's first observatory that is purpose-built from the ground up as an operational space weather observatory to provide trusted space weather data to safeguard society. Let me explain the context of why operational is significant. Historically, NOAA has measured the space environment using instruments hosted on satellites designed primarily to monitor Earth's weather, like our GOES-R series. And sometimes we've relied on data from NASA and European research satellites, or from Discover, a satellite which we retrofitted from a research demonstration mission. In contrast, SWFO-L1 is exclusively built for space weather observations, with satellite operations, instrument capabilities, and data refresh rates purpose-built to meet our specific operational objectives. And as the video showed, SWFO does 2 critical things in a single package. First, it monitors the sun to detect when storms erupt from the solar surface, ejecting plasma into space. We call these coronal mass ejections, or CMEs. And when Earth is in the line of fire, they're the most serious form of space weather storm. And second, positioned at Lagrange Point 1, a balance point between the gravity of the Earth and the sun, SWFO sits upwind of Earth and can measure the severity of these storms just a few minutes ahead of when they impact the Earth. Dimitris, our project scientist, will tell you more about it, but a short analogy that helps me as an engineer If a CME were a hurricane, our chronograph would be like detecting the storm's formation in the Atlantic. And you could think of SWFOL1's in-place sensors to be like hurricane hunters, measuring the intensity of the storm just before landfall. Incidentally, using that analogy, if the CME were scaled to the size of a hurricane, Earth itself would be only the size of a small neighborhood within a city. So these are very large events emanating from the sun. But from a programmatic standpoint, this has been really rewarding for me from the start until now, ready for launch. It's been a short development timeline from when we approved department baseline approval to launch is just over 5 years. And I'm proud that our strong partnership and shoulder-to-shoulder working relationship with NASA has been strong. Jim Morrissey will tell you more, but NASA has been an excellent acquisition agent for the program, providing exceptional project and engineering management expertise. And their oversight of the integration of NOAA's instruments with the spacecraft has been instrumental to the success of this mission. It's been an efficient program, and it's been really good vendor partnerships, a dedicated group of vendors assembled by NASA, led by spacecraft contractor BAE, with 4 instruments: the compact chronograph, developed by U.S. Naval Research Laboratory, the solar wind plasma sensor called SWIPS by Southwest Research Institute, the superthermal ion sensor we call STIS from UC Berkeley, and magnetometers from the University of New Hampshire and Southwest Research Institute. On the NOAA side, ground elements were upgraded to accomplish this mission. L3 Harris added the SWFO-L1 command and control system to our existing GOES-R series command and control system. And KBR built a robust antenna network at NOAA sites and with commercial services. But I want to hit this point again. Being operational is the game changer for forecast because of our commitment to low latency data. CME imagery is now going to be in the hands of the forecaster within 30 minutes, compared to up to 8 hours from our research partners. In situ measurements will be available within 5 minutes, and this will be transformative for the operational space weather forecasting. And programmatically, as Irene mentioned, we're not done. At Space Weather Observations in NOAA, we're committed to a future of observation continuity, and we're already in progress of developing SOLAR, the space weather observations at Lagrange 1 to advanced readiness, which is our next L1 observatory. We're planning to launch that as soon as 2029. America is the leader in space weather, and other nations are contributing to the success of this effort. In particular, Japan's National Institute of Communications Technology will be providing a data reception site at their Kashima ground station near Tokyo. Other international agencies have expressed interest and also some commitments to ensuring the success of this globally important mission. So in closing, SWFO-L1 launches no earlier than September 23. Go IMAP, go Carruthers, go SWFO. After a 3-month cruise and subsequent commissioning, we will be safeguarding society a million miles from home. Now, Dimitris will tell you about the science of space weather.
Thank you, Richard. Good morning, everyone. I'm the SWFO scientist, and I'm therefore responsible for the instrument data, and not only that, also for the quality of the products that are obtained by processing those data. So my job is to frequently communicate with the instrument developers, those teams that have built our state-of-the-art payload, and also the algorithm developers, the people who write the scripts that process those data. So what's so exciting about SWFOL1? This is a deep space mission that NOAA is deploying at 1 million miles from the Earth, or about 40 times the geosynchronous distance. And it will be our eye in the sky for solar storms that originate high above the surface of the star, but still have implications here on technology and on human safety, both in space and in flight. SWFOL1 will provide us with real-time images of the solar atmosphere and measurements of the solar wind and its particles. And one of the most remarkable things about the mission is that the data will have a wide range of users. It will not be limited to space scientists and space weather forecasters, all of whom the data will be valuable, of course, but they will also be used by satellite operators, electric power grid managers, GPS network managers, name just a few. And its images will replace those of a very well-known legacy solar satellite that is SOHO, which has been used also in research and education and other realms. There's also interest that's been expressed from international users, and we've seen that with other recent space weather projects. In other words, SWFOL1 will be a national critical asset and of utmost importance not only for NOAA and NASA, but also for the whole enterprise of space exploration. Let me back up a little bit and say, what is space weather? Like weather on the Earth, the weather in our space environment is determined mainly by the sun, the closest star. It includes detonations in its atmosphere, which are called solar flares, expulsions of magnetic fields and hot plasma. These are the coronal mass ejections that we heard about, and beams of fast-moving particles. Think of those like a hail of electrons and protons. These effects are far away, but they still have significant impacts on airline crews who fly on polar routes and astronauts who are in the space station. And they can also charge up sensitive electronics on board satellites and the space station and issue even phantom commands. Even those sound otherworldly, the effects can make their way to space and even on services on the ground. Speaking of that, the large magnetic fields generated in space can make their way to our upper atmosphere or ionosphere, and they can impact electric power grids, and their fluctuations can muddle GPS and telecommunication signals. So our growing dependence on satellite services and space-based technologies makes us vulnerable to these solar storms, and this is the main reason that NOAA is deploying these new capabilities. Finally, let me say what can be done as we predict these effects and what can be done to lessen the impacts of space weather. Similar to hurricanes and tornadoes, we cannot avoid space storms coming our way. These are overpowering and unavoidable events. And similar to those atmospheric effects, it's important to predict those as accurately as possible, when they start, how long they will last, and how severe each event will be. And these results will help operators, managers, and emergency responders implement plans of action that they've developed and practiced many times before. And so satellite operators, for example, can turn down several or turn off some segments of their satellites. Power grid managers can redirect transmission or distribution networks and protect vulnerable relays and transformers. And flight managers can direct pilots to new flight paths. Without that information, many of these systems would be essentially flying blind. Even the best models and the best humans in the loop would not be able to have enough information for accurate predictions. So in closing, like an eye in the sky or a weather buoy in this ocean, as we heard before, SWFOL1 will provide those accurate, reliable, and actionable information pieces to help us through the solar storms in this current and next solar cycles. With that, I'd like to introduce Shawn Dal for the Space Weather Prediction Center. Shawn?
Thank you, Demetrius. Hey, I'm excited. Thanks, everybody, for being here, because we at the Space Weather Prediction Center are extremely eager for the SWFOL-L1 spacecraft to not only launch, but get in position and start receiving its solar wind observations into our operations. Because this is a giant leap forward to our forecast and decision support services that we provide from right here at the Space Weather Prediction Center. We're going to receive continuous solar wind information from 1 million miles away in less than 5 minutes. What an amazing feat of engineering. Thanks to this new capability, we're going to be able to notify those critical technology operators and infrastructure maintainers that you've heard about, as well as many other key decision makers from the federal government level all the way down to a city, because emergency management needs to understand and know about space weather. And that's what we want to get, is give them the information they need with more confidence and better advance notice of impending solar storms. You've heard that this is going to be the world's first dedicated operational space weather spacecraft at the L1 orbital point. Previous spacecraft were research orientated or had secondary operational systems for space weather observing. But this set of instruments on SWFOL-L1 was specifically crafted for our ability to analyze the solar wind environment for changes that are going to better alert us for incoming space weather activity of importance. The satellite suite of solar, wind, and magnetic field instruments will have the latest technology for the most accurate and reliable measurements. Other instruments on the platform are going to give us an early indicator of potentially damaging solar radiation storms that could impact space flight and aviation globally. Even better, the satellite includes that compact chronograph that's going to increase our coverage for identifying coronal mass ejections that could arrive at Earth and lead to more intense storms that threaten the electric power grid to satellites in space. This coronal mass ejection that you see behind me happened overnight. Now it's from the far side of the sun, but this instrument, SWFO-L1, is going to give us information more reliably, faster, and directly into our operations to do all of this support that I've been talking about. The SWFO-L1 spacecraft is going to be a much needed and impressively new tool in our arsenal for improved space weather monitoring and prediction. That's not only going to serve the nation, but the entire world's needs and interests, because space weather is a global concern. So from farmers in the field to crucial system operators or even soldiers in battle, which can all be dramatically affected by space weather events in various ways, we at the Space Weather Prediction Center are going to be able to do an even better job of safeguarding society with actionable space weather information, thanks to the SWFO-L1 mission, which is going to be essential to helping us tremendously in that regard. So thank you very much. And now I'm pleased to bring in Jim Morrissey. Jim?
All right, thanks, Shawn. Great job there. So I'm just going to give you a little bit of background. I'm Jim Morrissey. I work at the Goddard Space Flight Center. I'm the NASA project manager for the observatory development, SWFOL1 Observatory. So as folks mentioned, I'm not going to go over things that other folks have said, but Rich mentioned, told you about our instruments. That work began in 2019 with the initial planning phase of SWFOL1. But really, we really got going in the summer of 2020 with the selection of Ball Aerospace as our spacecraft vendor. It should be noted that during that time, we were all remote with travel restrictions because of the pandemic. So one of the great things that happened was the team came together and we were able to stay on schedule during that time, during the subsequent 1.5, 2 years where we were working remotely. So that's sort of one of the things that the team is really proud of, that we were able to stay on schedule. Rich mentioned Carruthers and IMAP. Should be pointed out that we are rideshare. We don't. We're sharing we are secondary payload to the IMAP mission. IMAP and Carruthers are two other NASA missions that are launching with us on the SpaceX Falcon 9 rocket. One of the things another thing that happened, because we were a rideshare, IMAP had some delays, so we were able to use some of that time for some risk reduction activities on the spacecraft. But ultimately, we prior to shipping to Florida in July, we had been in storage for about 4 months, waiting for due to that launch delay. So the spacecraft is currently, like I said, we shipped in July. The spacecraft is currently fueled and ready for integration with the by SpaceX with the other missions, Carruthers and IMAP. There's it's called an ESPA ring. So we are, I think it's probably in the press kit materials, but we are one of 2 missions that are on this ring with IMAP located on top, and I think you'll see some of that stuff in the press materials. And we are ready for the September 23rd launch date. With that, Jim Mascarelli, who is our who managed the development of the spacecraft at BAE Systems. Jim, take it away. Thanks a lot.
Thanks, Jim. Hello, everybody. It's a pleasure to be here today. At BAE Systems, we're proud to deliver NOAA's first spacecraft dedicated to providing these early warnings and alerts for the space weather events that can impact Earth and our infrastructure. So yeah, as Jim was mentioning, about 5 years ago, in the midst of the global pandemic, we were selected to deliver this high-performance small spacecraft in partnership with NOAA and NASA Goddard. And our team gathered virtually from our living rooms, kitchen tables, basement offices. So we weren't just developing a spacecraft, but we were also figuring out new ways to collaborate, build up our strong team relationships when we couldn't meet in person. So we developed the spacecraft design and all the interfaces to the brand new instruments, pretty much all by remote work amongst our team here at BAE Systems and with our NASA, NOAA, and instrument partners. Then, as the pandemic started to wane, we faced new challenges, supply chain disruptions. That caused delays during assembly, integration, and test. I'm really proud of how our team worked together, not only here within BAE Systems, but with NASA and NOAA, our instrument partners. We adjusted the integration and test flow, came up with alternate approaches, kept everything moving forward through the observatory level testing. So reaching this point, ready for launch, it's really rewarding. We've trained the flight operations team, and after launch, we'll support spacecraft commissioning and mission ops. So we're really excited to continue supporting the mission and get this new capability up and running. So let me mention a few things about the spacecraft design. So SWFOL1 is built on our Evolve small spacecraft platform. So its first key feature is that it's engineered not only to survive solar radiation storms, but operate through them, which it has to do to meet its critical role of providing these timely warnings and alerts. We can't have our spacecraft going into hibernation mode during the solar storms we're supposed to be monitoring. And then another key feature is magnetic cleanliness. The spacecraft has to be magnetically clean so it doesn't corrupt the magnetometer's precise measurements of the solar wind's magnetic field. So this meant we had to consider the selection of every component, every bolt, the wiring on the spacecraft, surface finishes, and then follow special processes during assembly, integration, and test to make sure we maintain magnetic cleanliness and meet all those requirements. And then we demonstrated we met and exceeded those requirements in observatory level testing. And then finally, despite its small physical size, the spacecraft has a lot of capability. Besides hosting the 4 unique instruments, it includes a deployable boom for the magnetometers, a deployable and articulating high-gain dish antenna to stream the data continuously back to Earth, a robust attitude control system to keep the instruments pointed at the sun, and a propulsion system to get us to L1 and perform station keeping maneuvers while we're there. So that's a lot to pack into a small spacecraft. We were able to accommodate all this within our flexible, evolved spacecraft architecture. So we're excited to be part of the SWFO mission and continue our long-standing relationship with NOAA. We supported previous NOAA missions, including SOMOMI, NPP, NOAA 20, NOAA 21, and as was mentioned, we're also developing the successor to SWFO-L1, the solar spacecraft for the Space Weather Next L1. So we'll continue our support of NOAA's missions. So thanks again for having me here, and now I'll turn it over to Edward Uton of George Mason University.
Hello, everyone. Thanks, Jim. I'm looking forward to presenting some of our research to you today on the socioeconomic impacts of space weather on critical infrastructure. So one thing that we've been very active on over the past year or so is a new national assessment of the US focusing on the impacts of power grid failure from different space weather events. So I'll kind of put that into the context of what might happen, in terms of societal impacts and economic impacts as a way to really kind of justify the importance of the SWFO-L1 mission. So before I begin, it's just important for me to talk a little bit about the mechanism. So we've heard from Shawn and other folks about what happens when a CME is thrown out of the sun. But once it's passed through the interplanetary space and it starts to actually interact with the magnetosphere on Earth, due to Faraday's law of induction, we have geomagnetically induced currents which are actually produced on the surface of the Earth, the telluric currents. And in areas where you have very resistive rock, these aren't able to dissipate downward into Earth, and they pass through the into the extra high voltage power grid lines, essentially, because they follow the path of least resistance. Essentially, once they get to the substations, you have these very expensive, large, extra high voltage transformers that have this extra current being placed over them, and it can cause damage through thermal heating. It can cause voltage collapse, a wide-scale grid collapse, and that's a real big concern to us that we need to try to mitigate. So just to put that into context, in 1989, there was a very large event which took place in Quebec due to a space weather event, and the grid collapse in the Hydro-Quebec power outage area actually meant that most of the population had not very much power for about 48 hours. And if you were in a rural area or at the edge of the grid, it took up to a week, maybe 2 weeks to return power to you. So we know that these events do happen and that we essentially need to try to mitigate them. So one way that we've been doing that is by trying to link together the physics models with new engineering models of the power grid, and then also with the economic models that allow us to estimate these potential impacts. And I have 3 nuggets of statistical information for you based on the different return periods that we ran. So for 50 to 250 year return periods, we found that approximately 40 to 160,000 US businesses could be directly affected due to power outages. And that would roughly translate to about 1.5 to 6 million people who could be without power. Now, if we don't have power for businesses and people, this would translate to approximately a $250 million worth of daily losses, up to about $1.25 billion worth of daily losses in gross. The important thing to state is that we've used very conservative assumptions, which are supported through the best scientific evidence. So this isn't about posing trillion-dollar catastrophe scenarios that people might not believe. This is about using the very best evidence that we have. And even under these conservative assumptions, we identify that there are really substantial socioeconomic impacts, justifying investments into missions like SWFO-L1 and further space weather forecasting R&D. If we have that additional forewarning time, power grid operators, for example, can actually implement a range of mitigation measures within their grid. Okay, so they can do grid resequencing, they can island certain parts of their grid that they know is particularly vulnerable, and they can also implement geomagnetically induced current blockers, which they may have strategically placed around their network. So it's with that, I hope those kind of nuggets of information are useful for you to put this into a broader context. And I'll thank you all for your time, and I'll pass over to Captain John Dudley from American Airlines. Thank you.
Thank you, Edward. It is a privilege to speak today on the growing importance of an accurate forecast of space weather for general aviation and commercial aviation operators. As the Managing Director of Flight Operations and the Part 119 Director of Operations of American Airlines, I'm responsible for ensuring the reliability of our aircraft communications capabilities and our navigation capabilities. As an owner and operator of a smaller general aviation aircraft, I am just as motivated to ensure the reliability of the in-flight communication and navigation capabilities of my own general aviation aircraft. Active space weather can certainly create difficulties for us with both en route air-to-ground communications and airborne navigation. Many long-range aircraft today still use high-frequency or HF radios either as the primary or the backup communications equipment for long-range oceanic flying or flying over remote land areas. HF radio frequencies become quickly unusable following the arrival of a solar storm. With an accurate report from SWFO-L1 of the characteristics of an inbound solar event, we hope to soon be able to advise all aircraft using HF communications of the potential for the loss of comm capability and provide these aircraft with either alternate frequencies to use at predetermined points along their route or to select other onboard communication equipment for the remainder of their flight through the solar event. Concerning airborne navigation, since almost all aircraft today in both general aviation and commercial aviation use a form of GPS as their primary en route navigation means, the reliability of an accurate GPS position is increasingly vital. This topic becomes even more important each year as government-operated ground-based aircraft navigation aids, such as VOR stations for en route navigation and ILS approach equipment for accurate final approach and landing guidance, are decommissioned due to government budget constraints and equipment serviceability issues. GPS is used extensively today by small general aviation aircraft and large commercial airliners to guide us while we taxi out to the active runway and then take off and fly a precise departure route, climb out and cruise at the en route cruising altitude, and descend for the approach and landing, and finally the taxi in to the correct parking spot. Both on the ground and in flight, GPS is being used the entire time that an aircraft is in motion today. The accuracy of GPS for en route flight operations has become ever more important, with routes of flight near areas of geopolitical conflict around the world. We cannot afford in today's world to be miles off course from our planned and approved flight route. Also critical today is our need for GPS accuracy when flying an aircraft using a GPS-based approach and landing procedure into a mountain airport surrounded by high terrain, as is the case in many of our Rocky Mountain City airports here in the United States. With the future availability of an early warning of a possible GPS accuracy degradation from an inbound solar event, if we have an aircraft preparing to conduct a GPS approach into a mountain city and the weather conditions are marginal, we can notify the pilots to proceed to an alternate airport and advise them to not conduct the GPS approach into the mountain airport. As you can see, a warning of as little as 15 minutes of time until GPS degradation can potentially be very significant to us. We have a lot of more work to do to make timely solar storm event intensity information available to airline operations centers and government air traffic control centers so that we can properly alert flight crews of any downgrades in GPS accuracy over the next several minutes. We see the arrival of technology like the SWFO-1L satellite as an important step in obtaining and distributing timely and accurate solar event information throughout the aviation community. And now we will hear from Terry Griffin, professor and extension economist at Kansas State University.
All right, thank you, Captain. One quick, if you don't mind me jumping in here, Terry. I did want to remind folks that we do have a Q&A box at the bottom of your screen. You'll see it right there. We'd like you to type in your name, your question, your affiliation, and potentially the expert you'd like to answer that question, if you know who that would be. I just want to remind folks as we're getting to our last presentation from Dr. Griffin right now. Thanks again, Captain. And Dr. Griffin, go ahead, please.
Thank you, John and Captain. It's an honor to be here at Kansas State University today. I'm going to say some things that may hit you where it hurts, in the stomach and in the pocketbook. Global navigation satellite systems like GPS have many civilian uses across industries such as construction and mining. Today, I'm going to discuss their application in food and fiber production. According to the 2023 USDA ERS Precision Agriculture Survey, GPS is used on 2/3 of U.S. farmland for automated guidance and data collection. Automated guidance enables parallel passes through the field. It's a form of self-driving technology that's now standard on many farms. GPS is also used to georeference sensor data, yield, moisture, soil properties. And with the rise of drones and unmanned aerial systems, GPS has been used for an expanding set of niche but critical tasks, all of which rely upon accurate location and wireless connectivity. GPS hasn't just been helpful for agricultural productivity. It's become so integrated that removing location information disrupts operations to the point of economic damage, and we've seen that play out. Last year, on May 10, 2024, GPS signal degradation occurred, caused by space weather known as the Gannon storm, led to delays of 4 or more hours displacing acreage into later planting weeks with lower yield potential, especially for parts of the Corn Belt that were already behind schedule. Conservative estimates suggest nearly $1 billion in lost corn production across the Midwest as far south as Kansas. And not all crops are affected the same way. Take peanuts, for example. Peanuts are dug from underground during the harvest process. And during signal loss, farmers face a difficult choice. Do they continue planting without sub-inch accuracy, or do they wait until GPS is fully restored? The answer depends on how long the outage will last, and that's exactly where SWFO-L1 can help. Not by predicting when an outage will happen, but by providing a reliable nowcast. When will the current GPS outage be over? For crops like peanuts, that's the difference between a good decision and a costly mistake. It may sound nuts, but GPS outages were reported as far south as Georgia, where the majority of peanuts are grown, nearly $800 million worth last year. And during peak planting times, the expected value of a nowcast is $20 million. A reliable nowcast is worth over $30 million across the southeastern United States just for peanuts. Farm GPS outages are real and will happen again. With reliable nowcasts, farmers can mitigate some of these risks. Accurate nowcasts save crops, money, and livelihood. Back to you, John.
Thank you so much, Terry. Great talk from everybody. Thank you so much, everyone, for participating today and giving us some great feedback. And I'm really learning a lot about the impacts of space weather. So thanks again. So now this is the time when we take questions from the media. Just as a reminder, we do have a Q&A box located at the bottom of your screen. Please type in your name, your affiliation, what your question is, and the specific expert who you'd like to answer the question, if possible. We already have one. I think Jim Morrissey, this might be a good one for you. It's a two-part question. How long will it take the satellite to reach L1 orbit, and when is SWFO-L1 expected to become operational?
Okay. All right. Yeah, good question. So it takes us about 150 days to get out to, 115 days to get out to L1. Once we're there, we have to get into our orbit. So we orbit about that point in space. That's a stable point between the Earth and the Sun. It takes us we have about 18 days worth of maneuvers before we are finished and in our operational orbit. So we're looking at being operational in about the February 2026 timeframe.
Okay, thank you so much. Next question looks like it might be for Demetrius. How will the compact chronograph on board SWFO-L1, we call it the SEACOR-2, how will that differ from the one that's currently on board NOAA's GOES-19 satellite, the SEACOR-1?
Thank you, John. The two chronographs that the Naval Research Laboratory built for us, for NOAA, are nearly identical. The only major difference is what's called the field of view, that is the amount of sky area that they can pertain and record. SEACOR-2 has a larger field of view. That means that it can actually track these damaging disturbances, the coronal mass ejections, for a longer time. That enables us to obtain better estimates of their terminal velocity and therefore their arrival time here on Earth. So it will be complementary to the existing SEACOR-1 observatory, but with that additional advantage. Now, to compensate for that, SEACOR-2 will have a slightly lower angular resolution, but that's not expected to reduce our observational capability or the accuracy of our predictions. These are the two major differences between the two instruments.
All right. Thank you so much, Demetrius. The next one, I'm thinking this might be for Shawn, but Shawn, you let me know. This is from Corina Capablanca from Spectrum News. Have space weather events been increasingly impacting Earth, or have we just been noticing them more because of our increased reliance on GPS?
Yeah, thanks for that question, Corina. It's hard to give an answer for that precisely, but what I can talk to is what's happened, so far this solar cycle. Solar cycle being roughly an 11-year period of time on average, where we have a maximum of activity. Well, we've been in that solar maximum for this cycle. Last year proved pretty active when it came to these geomagnetic storms. But because of the decision support that we provide, the warnings and alerts that we put out there, and communicate directly with all these infrastructure operators, from the electric power grid to aviation to hopefully eventually in some capacity farmers in the field, even as they learn and understand this importance of this more. The effects we have on our technology, yes, they are noticed. The electric power grid was extremely busy during particularly this storm, the Gannon storm, the May 2024 storm of last year. We gave them hours of notice thanks to some confidence levels we had. We think we can do even better with that with SWFOL1 and improve on that. But they're able to take a lot of mitigating measures because of the advance notice we give them. They can't do it when we give them just minutes of notice, but they can do it when they have hours of notice. And they did that. There were a lot of issues. There were high voltage capacitors that tripped during that storm, but no bulk transmission failure. But this G5 level, this extreme level storm, was kind of just in there. So it was a good test case for us. This was not to the level of the 1989 storm that you heard about, and it was way short of the famous Carrington event of 1859. And now we have satellites all over the place in space. Satellites are impacted dramatically, especially low Earth orbiting ones. Some of the largest satellite migration in history happened with the May storm until it was surpassed by an even less severe storm in October of last year. Over 5,000 satellites burning fuel at the same time to maintain their orbit because of the changes this does to where they operate. They will burn up in the atmosphere if they're not accounted for. So yes, a lot more going on these days, and all these sectors are communicating with us more and more as they learn about space weather, understand it, and use it. So the concern continues, but the advance notice that we're able to provide with improved capabilities for coronal mass ejections like you see behind me here are extremely important to helping that success story.
All right, thank you. And this one does not have a great answer, by the way, Shawn. Thank you. This one doesn't have anyone in particular answer, but this might be something you could follow up on, because the next question is, how will SWFOL1 improve on our abilities that as compared to what we currently rely on from our satellites?
Yeah, I'll speak to us from the forecast office. It's a dramatic improvement. We've been relying on research satellites. The one you see behind me is a NASA research satellite that's decades old. Yes, the imagery looks good. You can clearly see the CME, but a lot of these we can't see well, and we can lose imagery periods of time for hours because it's not an operational satellite. What SWFOL1 is going to do is, from beginning to end, we're going to see things like coronal mass ejections go through space. First, the chronograph is going to detect it, and we'll observe it within 20 minutes. We'll have an updated image of a CME progression as it moves out, like you see behind me here. Then we can get a watch ready after we analyze them and decide when or if it may hit Earth. Then we wait for it. And thanks to SWFOL1, then we'll see it arrive 1 million miles from Earth. So we'll know it's within minutes of arrival here to our planet to begin storming. That's when we can put out warnings. So now we can do a better job with watches, thanks to the chronograph, and then we can do a better job with warning timeliness and accuracy, thanks to the instrument package that's measuring the solar wind environment. So all in all, this is a one-stop shop, great for that million-mile point in space to us. And then with the other fleet of equipment that we have on the GOES satellites, this just adds to our ability to do a much better job for forecasting and doing warnings and alerts for the industries.
All right. Thank you so much, Shawn. Great answer again. I appreciate it. I do not have a name or affiliation for this, but Ed, I've got a question for you. You mentioned Quebec. Are there risks? Are these risks mainly at high latitudes for power concerns?
Thanks, John. So at high latitude, you will see larger activity. But if there was a really large event like a Carrington, the auroral electrojet would move equatorward. And that would mean that mid to lower latitude areas would be potentially affected. And we're quite concerned about complacency among power grid operators in those regions because they're not used to seeing or dealing with space weather on a regular basis.
Great. Thank you so much for that, Ed. The next one, and I hope I'm pronouncing the name correctly, Daisy Dobrevec from space.com. The satellites currently monitoring space weather from L1, such as ACE, SOHO, and Discover, are decades old and operating past their design lifespans. How urgent is it to get SWFO-L1 in place before these aging spacecraft fail? And what would happen if we had a gap in coverage? Who would like to take that one?
I guess I could start with that. I mean, from a programmatic perspective, this is part of what drove the urgency of the SWFO-L1 program. The idea that we could get a rideshare with IMAP, which had been scheduled, and that we could develop this capability in time to meet that rideshare time. Yeah, it's extremely urgent. These satellites, ACE, SOHO, Discover, are all working beyond their design life. You may know that Discover went into safe hold several weeks ago. We're trying to recover it, but the need is urgent, and we must replace this capability now.
All right, thank you. We did have a quick follow-up from Daisy from space.com. Is there discussion of future successors or a constellation of satellites at different Lagrange points in the future?
Well, actually, yes, there is. As mentioned, we've already started the development of the spacecraft we're calling Solar A, which will be launched in 2029, we hope, and that would have a similar instrument complement to SWFO. So that covers Lagrange point 1, where we have a commitment to have continuity of these critical measurements. We're also working with our international partners to get off Sun-Earth line measurements, and the ESA Vigil mission is scheduled to launch, I believe, in 2031. We are providing CCOR3, our third compact chronograph, to ESA to be on that spacecraft, and that will give us a stereoscopic view of coronal mass ejections as they come out of the sun. ESA will be putting other instruments, other space weather observing instruments on the Vigil mission, and those will be very useful for us as well.
All right, thank you, Richard. Karina Capablanca from Spectrum News had a quick follow-up question for whoever wants to take it. What is the price tag for the SWFO-L1 satellite?
I can go ahead for that. So the life cycle cost for SWFO through operations is approximately planned to be $692.8 million. Again, that is including the life cycle cost, and it also includes the compact chronograph that went on to GOES 19, GOES-U, and the compact chronograph that's going to ESA.
All right. Thank you, Irene. We had another one for from Samantha Watson for Captain John. Do commercial pilots receive any required space weather training? And are you aware of any training for GA pilots, which is that general aviation?
Yes, that would be general aviation, John.
Okay,
thank you. Samantha, thank you. Very nice speaking with you. Yes, commercial airline pilots do receive training in space weather events and the possible effects on GPS navigation and communication, of course. So we do receive that training initially, and then from time to time we receive additional follow-up training in our recurrent training at the airline, which occurs each year for all of our airline pilots. In general aviation, it's also taught when a pilot is learning about GPS equipment and how approaches are flown, and the data that must be monitored to ensure accuracy during a GPS approach. We look at different ways that accuracy could be reduced. So that's what we do. So we actually do cover this training in both commercial aviation and general aviation. Thank you again for the question.
Yeah, and thank you, Captain. It does not appear that we have any more questions. We do have about 5 minutes left in this briefing. So real quick, I'll just put out the call again. If you do have a question, we have the Q&A box at the bottom of your screen. Just type your name and affiliation in there. And I don't see anything else coming in. So at this point, Unless I see anything popping up while I start to wrap things up, I just want to thank everybody for their time, especially our presenters and all the participants that came in today. As a reminder, for those of you who were not able to get all the information down as it was presented to you, there is a recording of this media briefing that will be available online later today at NOAA Satellite's YouTube channel. I also remind folks, if you look at the bottom left of your screen, those are links for more information that you can quickly link on right now before we end this briefing. One is for more information about SWFO-L1 in general, and the other is the press kit, which has a lot of great press goodies in it, so please check that out. And as always, if anyone from the media has additional information that they need, you can reach out to me, John Bateman, at NESDIS.pa at NOAA.gov, and that email address is also on the media advisory for this briefing. And thanks so much for joining us.
Thanks, everyone.